Assalamualaikum, we are from Group 5. We are presenting our experiment on gas chromatography. Before that, let me introduce you our group members. My name is Nur Umairah Shadia. We have Nur Hanisa Safia, Anisa Dahia, Nur Ramizah and Nurul Amalina. So what is gas chromatography? It is a powerful analytical separation technique used to isolate, identify and quantify volatile chemical component within a complex mixture. The fundamental theory relies on the differential partitioning of analytical molecule between a vaporized mobile phase, typically an inert carrier gas like helium or nitrogen, and a stationary phase contained within a heat column. As the sample is injected and vaporized, its components are carried through the column, which compound with a higher affinity for the stationary phase are retained longer, while those with a higher affinity for the mobile phase elute more quickly. This separation is driven by molecular properties such as a boiling point, vapor pressure and chemical polarity. A detector at the column outlet records the emerging chemical fraction over time, generating a chromatogram where each distinct peak reflects the specific retardation time and relative concentration of a separate compound. Let's move on to our core objective of this experiment. First, we aim to determine the specific retardation time of two target compounds, which is N-butanol and 2-propanol. Second, we use this retardation time to identify the individual components present within a standard mixture. Third, we applied this baseline data to successfully identify the unknown component present in our given sample. And finally, we investigate the effect of temperature on both retardation time and resolution.
Next, I will explain the GC instrument using the flowchart and the schematic diagram. First, according to the flowchart, the process starts with the carrier gas, which moves through the flow controller. The flow controller regulates the gas pressure and flow rate to ensure stable operation. The sample is then introduced through the injector, where it is quickly vaporized before entering the system. Next, the sample travels through the column, which is located inside the oven. This is where the separation of compounds takes place based on their different interaction with the stationary phase. After leaving the column, the separated compounds reach the detector, which converts them into electrical signals. Then signals are then sent to the computer, which processes the data and produces a chromatogram. Each peak on the chromatogram represents a different compound in the sample. Moving on the schematic diagram, the carrier gas first passes through a pressure regulator and flow controller before entering the injector. The vaporized sample then moves through the coiled column inside the oven, where separation occurs. The separated compounds are detected by detector, and finally the signals are processed by the computer to generate the chromatograph for analysis. Next, I will explain the procedure of this experiment. First, for the chemical use, we have 2-propanol and butanol, a standard mixture containing both compounds, and an unknown sample for identification. The apparatus used include a shrink, beaker, and dropper. For the sample handling step, the shrink must be rinsed several times with the sample to avoid contamination. Any air bubbles should be removed, and the sample volume should be adjusted to the eye level before performing a quick injection into the GC system. Moving on the experimental and the operation process, the GC instrument is first switched on and the operating conditions are set. In this experiment, the initial oven temperature is 70 degrees Celsius, while the injector and detector temperatures are maintained at 180 degrees Celsius. The carrier gas, which include nitrogen, hydrogen, and purified air, are supplied to the system. Nitrogen acts as the carrier gas, while hydrogen and air support the flame ionization detector, or FID. The individual standard compounds are injected first to determine their retention times. Next, the standard mixture is injected, and and the peaks are identified by comparing their retention time with those of the pure compounds. Finally, the unknown sample is analyzed to determine the components present. To study the effect of temperature, the oven temperature is later changed to 100 degrees Celsius and 140 degrees Celsius, and the retention time and resolution of the components are observed. The detector converts to the separated compound into electrical signals, and these signals are amplified and sent to the computer. The computer then plots a chromatogram which displays detectors respond against time, where each peak represents different compound. On this slide, I will explain the main components of the gas chromatography or GC system. First is the carrier gas, which acts as the mobile phase. It carries the sample through the columns. Common carrier gases are helium, nitrogen, and hydrogen. Next is the injector. This is where the samples enter the GC. The injector is heated so the sample quickly changes into gas before separation begins. The third one is the sample then move into the column, where the separation takes place. Different compounds travel at different speeds based on their interactions with the stationary phase. The fourth is the ovens controls the temperature of the columns. The temperature affects the retention times and the quality of the separations. Fifth is the flow controller, regulates the pressure and flow rate of their carrier gas. A stable flow is important to obtain accurate results and good peak shapes. The sixth one is after separation, the compounds reach the detector. The detector converts the compounds into electrical signals, and the signal strengths depend on the amount of the compound present. The signals are sent to the amplifier, which makes them stronger so they can be recorded clearly. Finally, the data system displays the result as a chromatogram, which is a graph of detector response against time. Each peak on the graph represents a different compound. That's all.
This slide shows the gas chromatography results for the standard mixture at three different column temperatures, such as 70, 100, and 114 Celsius. As the column temperature increased, the retention time of both compounds decreased. At 70 Celsius, the two peaks appeared at 2.67 minutes and 5.81 minutes. At 100 Celsius, the retention time decreased to 2.27 minutes and 3.28 minutes, while at 114 Celsius, they further decreased to 1.95 minutes and 2.2 minutes. This happened because increasing the column temperature increased the vapor pressure at the analyte. As a result, the analyte spent less time interacting with the stationary phase and intuited faster through the column. We also observed that the gap between the two peaks becomes smaller as the temperature increased. At 70 Celsius, the peaks were widely separated, giving excellent resolution and a longer analysis time. At 100 Celsius, the peaks were still well separated while the analysis time was shorter, providing a good balance between separation and efficiency. At 114 Celsius, the peaks eluded much closer together. However, they remained clearly distinguishable and did not overlap, indicating that the separation was still acceptable. In addition, the analysis time was the shortest at this temperature. Overall, increasing the column temperature reduced the retention time and analysis time, while decreasing the gap between the peaks. Among the three temperatures, 100 Celsius.
For these slides, we analyzed the chromatograms at 70 degrees Celsius. Based on the results, 2-propanol showed its major peak at approximately 2.707 minutes, while N-butanol showed its major peak at approximately 5.956 minutes. The difference in retention time is due to their different volatility and boiling points. Since 2-propanol is more volatile and has a lower boiling point, it travels through the GC column faster and elutes earlier than N-butanol. Next, when we compare the unknown sample with both standards, the major peak of the unknown sample is closer to the retention time of N-butanol. Therefore, we can suggest that the unknown sample is most likely N-butanol. However, retention time comparison only provides tentative identification, so additional confirmatory analysis may be required for definite identification. Overall, the result shows that 2-propanol elutes earlier than N-butanol, and the unknown sample is most likely N-butanol.
In conclusion, the objective of the experiment were successfully achieved. The retention time of 2-propanols and N-butanol were determined. The 2-propanol show a shorter retention time at 2.707 minutes, while an N-butanol show a retention time of around 5.956 minutes, both at 70 Celsius. This due to the high vitality and lower boiling point. In addition, the unknown samples was identified as an N-butanol because it closely matched or almost similar to N-butanol standards at around 5.956 minutes. Furthermore, what we can see in this experiment, increasing the column temperature from 70 Celsius to 140 Celsius will decrease the retention time and shorten the analysis time. Although the field resolution was reduced, acceptable separation was still maintained, and overall, what we can see, a gas chromatography was proved to be an effective technique for separating an identified volatile compound based on their retention time behavior.